Good evening, one and all, for the 9th day of webinar series, Advanced Water and Wastewater Treatment. So today we have an eminent person from India, not from abroad, Professor Parag Gogate from ICT Mumbai. So among the researchers in India, I think a few well-known persons, worldwide well-known persons are there in my personal opinion. One is Parag Gogate, another one Professor Vasudevan from Sikri, Karakudi, and a few. So today, last a few sessions, we heard about the chemical reactions that involved for the generation of hydroxide radicals for the treatment of or degradation of various organic pollutants, or even for some cases for normal treatment of arsenic and all. Today, we will discuss about a mechanical way of producing hydroxide radicals in water and its treatment mechanism. It is commonly known as hydrodynamic cavitation, and two persons are famous from India for these reactions or this type of process. One is Parag R. Gogate and next one is A.B. Pandit, and both are from ICT Mumbai. So before starting the program, I will introduce Professor Parag Gogate. Professor Parag Gogate completed B Chemical Engineering and M Chemical Engineering, that is bachelor's and master's Chemical Engineering, and PhD. Three are from Institute of Chemical Technology, ICT Mumbai, and now he is currently working as professor in Chemical Engineering at ICT Mumbai. The main research interests of Parag Gogate includes cavitation phenomena, that means including acoustic cavitation, then wastewater treatment, design of multi-phase reactors, separation process, and process intensification. Professor Gogate has published over 300 research papers in international journals and has also written 25 chapters in books. Professor Gogate is a well-cited researcher with over 14,600 citations and H-index of 64 as per Scopus. And as per Google Scholar, it will be more around 20,000. Professor Gogate has given over 90 invited talks or seminars globally and also participated in 20 international conferences. Professor Gogate is also consultant to few industrial organizations in the area of process intensification, process involvement, and wastewater treatment. Professor Gogate has been involved in international collaborations with groups in Germany, France, Hungary, Portugal, Brazil, and Ukraine. Professor Gogate has also a visiting associate professor at Purdue University, USA in 2010. Now he is also serving as an associate editor for Chemical Engineering Journal Intensification, Process Intensification, elsewhere publications. So Professor Parag Gogate, please.
Yes, thank you, Dr. Nilesh, for the introduction. And let's start discussing about hydrodynamic cavitation. So I'll share the screen, and so the slides would be visible. And then let's make it full screen. Right, and so today we are going to listen to hydrodynamic cavitation, which we consider it as a novel approach for water and wastewater treatment. Now, if you look at the history of cavitation, it was majorly to avoid generation of cavitation, and that was in hydraulic devices, because many of you would quickly realize that cavitation in hydraulic devices gives you erosion of the materials, and definitely we would want to avoid it. Before going into the engineering aspects and how it can be applied, let's see how nature is also utilizing cavitation. This is an interesting study which was done at University of Twente. So it's a snapping shrimp which they captured it based on high-speed image capturing. And you can clearly see that this is the jaw, which is oscillating at a very high speed. Now it's a slow motion recording, but it is interesting to know in this particular top view that something is being thrown when the jaw closes. It's traveling a certain distance and then it's basically disappearing or it's collapsing. Now, if you do a pressure mapping around different regions, then these are the different regions which are mapped. So point 1 is basically the snapping shrimp itself. Point 2 is the release of this particular cavity. And then look at point 3, there is a sudden increase in the sound pressure which is recorded. Now these numbers may not be significant, but for the prey which is going to be around snapping shrimp, it definitely encounters a pressure burst, and then the objective is met. So what we want to do is try to replicate this natural phenomena at multiple locations in the reactor. Of course, I had already said that it can also give you erosion of propeller blades or hydraulic devices in which it is being generated. So the engineer's job would be definitely to control it in a proper way. So concentrated efforts, as you have also heard from Dr. Nidish earlier, by a few research groups has been towards harnessing the positive effect of hydrodynamic cavitation. Now let's see how we can generate it. So imagine a simple pipe flow where you can insert certain constriction. Now this constriction can be a simple throttling valve. It can be a single hole orifice or a multiple orifice plate. It can be a venturi as well. Now each of these devices is going to give you some advantages, some disadvantages. And what happens is your classical Bernoulli's principle, as soon as you have reduction in the flow area, the velocity is going to go up, the local pressure is going to go down, and if this local pressure falls below the vapor pressure of liquid, then you are going to generate cavitation at the point of vena contracta. As it goes downstream, definitely you will get the pressure recovery, and then the cavitation is happening. And the final collapse definitely is going to give you desired effects. Now, different types of cavitations can be generated, as I said, based on the use of different cavitating devices or operating conditions. So here are two distinctly different types of cavitation events which can be generated. One is a steady collapse, and second is a transient collapse. Now, transient collapse, you can clearly see that it's reaching to a significantly higher intermediate size. This is radius on the y-axis, and it's collapsing very fast. But there is only one cycle, whereas in the case of steady cavitation, you get multiple such cycles. Now, what will be different is the cavitational intensity, which is going to be generated in steady cavitation or in the case of transient cavitation. Now, in the case of transient cavitation, it's going to be much more intense. And you can clearly see in this video as well that the bubble collapse is introducing jet flow, and then some amount of solid dispersion can happen in the case of transient cavitation. In the case of steady cavitation, there is no such effect. You are just getting intermediate pressure pulses. Now, as I said, the cavitational intensity is going to be different. And also the energy requirement to generate these cavitation is also going to be different. So you need to match the requirement with the desired energy consumption, because finally, depending on the application, your cost of treatment is going to be extremely important. So I don't want to spend too much of energy if it is not required. And again, depending on the area, we had said that it can be either used for water treatment or for wastewater treatment. Now, in the case of water treatment, if you are just talking about microorganisms, then you don't really require significant energy as compared to what you require for oxidation of chemicals. So for oxidation of chemicals, like you're treating the leather industry effluent, definitely you would want transient cavitation to happen. But if you're looking just as microbial disruption, then even steady cavitation might be a good idea. And of course, the cost of treatment is going to be different in these two cases. Right, so what we look at or what we get in cavitation, you get localized intense pressure and temperature conditions. You have production of highly reactive free radical. So if water is present, then you will get hydroxyl radicals, which all of us know that are very strong oxidizing agent. If you are adding some amount of hydrogen peroxide, then again that can dissociate and give you hydroxyl radicals. So I'm going to get oxidizing species, which can definitely give me enhanced oxidation capacity. You also have high intensity turbulence, and you have increased transport coefficient, which will give you enhanced mass transfer, and then definitely the effects are going to be significant. There is a concentrated energy dissipation at the location of transformation. So this also is going to be beneficial depending on what application you are looking at. So if I combine all this, definitely I'll get an order of magnitude reduction in the energy requirement for any physical chemical transformation. Now this is a broad slide in terms of what are the effects in cavitating zone. Depending on the application, we just have to rely on only some effects. Like if it's oxidation, then definitely radicals formation, the local hotspots are going to be very important. But if it's just a kind of extraction related application, then I would require high intensity turbulence or increased transport coefficient, also equally important. So in short, we need to tailor the effects depending on what applications you are looking at. Now this high intensity turbulence and increased transport coefficient is also going to be useful when I'm talking about hybrid methods. Now hydrodynamic cavitation itself may not be efficient, but you can combine it with other methods, and we are going to see some examples in the later part of this talk. So there your turbulence and increased transport coefficients are also going to be very important. Right, we have started the discussions saying that hydrodynamic cavitation can give you erosion as well. So you might ask, what happens to my reactor? So there is the job for all of us as engineers. We need to control the phenomena and try to use the effects in a positive way, meaning my reactor should be protected and only the cavitation events should happen in the liquid, giving you effects, but the overall erosion should not happen. So that is what we need to achieve. The quick outline of this talk, we'll see some concepts, reactor designs which can be applied, water disinfection treatment, some case studies from effluent treatment. These are mainly based on work we are doing at ICT. We'll also look into combined processes and then some concluding remarks. So look at what reactors which are available. So you have high speed or high pressure homogenizer. These can also act as hydrodynamic cavitating devices. All you have to do is just try to construct a simple loop. So you will see that most of the hydrodynamic cavitation reactors would be operated as loops. So you'll have a feed tank, then you have the first stage or second stage or multiple stages of hydrodynamic cavitating devices. So I have written here as homogenization, but it can be even applicable to the other reactor configurations. And then you are going to recirculate it back. So your treatment time will depend on what are the initial conditions for your effluent, and then you can decide on the mode of application. It can also be a single pass treatment because some of the treatments would require only single pass, may not be efficient to keep on recirculating, especially for huge volumes. There you might have to design your reactor properly so that you get the desired benefits only in one pass through your cavitating device. Let's look at orifice plate setup. Again, similar recirculation type. You have a feed tank, then you have a centrifugal pump. It can be also a plunger pump. You are going back through this particular main line. This is the cavitation device. And then you also have what is described as a bypass line just to control your pump characteristics and allow good recirculation of the entire treatment volume. So I can have different designs of cavitation chamber. So I can use a venturi. I can use again a slit venturi or a circular venturi. I can use an orifice plate. The orifice plate also, it's simple depicted as single hole on the orifice plate, but you can have multiple holes on plates. It can be of different shapes. It can be of different sizes and whatnot. So orifice plate, as far our experience goes, has offered tremendous flexibility in terms of how you can control the cavitational intensity. Of course, the pressure drop is going to be higher because again, it goes back to your engineering days, undergraduate days, where you must have done experiments and said that the discharge coefficient for venturi is greater than 0.9. For orifice plate, it's going to be between 0.5 to 0.6. So definitely your pressure drop is going to be much high in the case of orifice plate as compared to Venturi. What it also means is your pumping energy required is going to be higher when you're using orifice plate, but that is also providing you higher cavitational activity. So again, depending on what you want to do, you can have a good balance between cavitational intensity and whatever energy requirements you are going to do. In the case of orifice plates, I was just talking, you can have a variation in terms of the number of holes and also shapes. Now, experimentally, what we have seen is it is quite easy to drill circular holes, but you can theoretically, you can even think of triangular holes. You can also think of rectangular, square holes, hexagonal holes. What is going to differ is your perimeter as compared to flow area. Now, flow area is going to decide your intensity of cavitation, and your perimeter also is going to decide the active cavitational zone which is going to be formed. So again, a balance can be made, but whatever experiments we have done, mostly these are based on circular holes and of different configurations. You can also have hydrodynamic cavitation setup based on stator rotor type. So you can have a rotating cylinder with holes, and then you have a cylinder with casing in a side view, and you generate a lot of turbulence in the system, but essentially it still remains as a recirculation mode where cavitating device is mentioned here. Let's look at some of the theoretical aspects, because we may not want to actually perform experiments with different cavitating device. So some aspects, theoretical aspects like bubble dynamic simulations, can really be useful in terms of deciding whether what should be my optimum geometry to get maximum effects. So you can solve different equations like a single cavity approach, you can have a cluster approach, you can numerically optimize the cavitation reactors, and then we'll have some guidelines based on this. A basic way to decide whether cavitation is happening or not is to calculate the cavitation number. So you have pressure drop per unit kinetic energy. So P2 is recovered pressure, PV is the vapor pressure at the given operating temperature, and V0 would be the velocity at the orifice or whatever constriction you are using. So ideally, when CV is less than 1, you will have a lot of cavitation. Presence of dissolved gases, impurities might result in cavitation at higher cavitation numbers as well. But for maximum benefits, I should maintain it below 1. The ideal recommended range based on whatever experiments we have done is about 0.1 to 0.4. Below 0.1, you don't want to operate because it generates too many cavities, and then you will get a cushioning effect, which is reduced cavitational intensity. So the typical range is 0.1 to 0.4. So again, I need to solve my bubble dynamics equation. So this is just the velocity profile and the pressure recovery. So you can have pressure recovery based on without turbulence or with turbulence. Definitely turbulence is going to occur. So I can get the pressure field distribution as a function of time, as a function of location in the downstream of the orifice, solve these particular equations, and these are the classical bubble dynamics equations which we have solved. Rayleigh-Placid equation is a basic approach for cavitation, and you also have the compressibility equation which can be solved. So here P infinity, wherever it is mentioned, that is the fluctuating pressure field which was given in the earlier equation based on turbulence. So typically, again, you can solve for a particular set of operating conditions. You can generate steady cavitation. So numerically, you can decide under which conditions you are likely to get steady cavitation. And so depending on the application, I might want to select conditions which can give me steady cavitation or which can give me transient cavitation. So definitely that whatever we had seen earlier can be reproduced based on numerical simulations. Right, so any bubble dynamic simulation will give you the instantaneous values of radius, the bubble wall velocity, acceleration, pressure and temperature inside the bubble as a function of different liquid physicochemical properties. And I can just quantify the cavitational intensity based on this. if I link it to some chemical reaction, I can also predict what is the number of free radicals which are going to be generated in the system. So this was one of the earlier works which we did, and based on numerical simulations, we tried to arrive at best conditions. So if I'm talking about liquid physicochemical properties, typically liquid with low vapor pressure is going to be useful. Low viscosity definitely is going to be a requirement, because what we have seen is if I'm using higher viscosity in the operation, then my cavitation is very limited. So I don't want to use maybe high viscosity oils, because my cavitation is going to be limited. Of course, when I'm looking at water and wastewater treatment, water satisfies all these favorable conditions. So you have already low vapor pressure, you have low viscosity, low surface tension, you will have ambient conditions to be used for wastewater treatment. So definitely lower temperatures are preferable. So these are some of the aspects. In terms of orifice plate, I have already said that cavitation number less than 1 is desirable. Typically, I need to operate at higher inlet pressure, which will give me intense cavitation. But again, it should be optimum so as to avoid my super cavitation, which we call as too many cavities being generated in the system. And you need to use plates, orifice plates, with typically smaller size of holes and large in number, because that's going to give me benefits of shear layer. In essence, your cavitationally active volume in the reactor is going to be higher. So I can basically recommend orifice plate for intense chemical reactions. So for oxidation or wastewater treatment, definitely orifice will be more suitable. For milder processes, typically venturi will be suitable. Again, we have said that pumping energy is going to be higher in the case of orifice as against venturi. So that balance needs to be maintained. So for stubborn reactions, again, it talks about some reactions as well. So in our wastewater treatment, this would ideally transform stubborn reactions, meaning you have a high load of COD, then your higher cavitational intensity will be required. If you have lower COD, or you just want to use hydrodynamic cavitation as a pre-treatment, then I would say that only mild treatment is going to be beneficial. And then I can also select lower discharge pressure or venturi as my cavitating device. How I can increase the cavitational intensity? Again, some geometric recommendations are given. So I can reduce the length of venturi or reduce the venturi throat to pipe diameter ratio. In the case of orifice, definitely I can increase the pipe size, and then downstream of the orifice, which will increase the pressure recovery, leading to higher cavitational intensity. I can also increase the number of holes or decrease the size of holes. So these are just some recommendations based on whatever design or theoretical simulations have been completed, and these are the guidelines which you can use during the design. Let's see now some experimental results, because I think you might have heard about ultrasonic cavitation or acoustic cavitation, using ultrasound to generate cavitation. And remember, this hydrodynamic cavitation was proposed as an alternative to ultrasonic cavitation, because ultrasound does offer a lot of limitations, especially on larger scales of treatment, and for wastewater treatment, where cost is going to be significantly important. So there I may not want to use ultrasound. Of course, ultrasound does have advantages in terms of higher cavitational intensity. For solid presence of solids, ultrasound may be more suitable, because in hydrodynamic cavitation you would have a problem. But let's see some case studies where I'm comparing hydrodynamic cavitation with acoustic cavitation. So again, the initial study was based on nitrophenol. Nitroaromatics, substituted aromatics are having more toxic effects. So we compared it with cavitational yield, which is a parameter to compare the moles degraded per unit energy supplied. So in the case of acoustic cavitation, about 7 liters of operating volume, 1 kilowatt as energy dissipation rate, and 90 minutes of treatment, you get cavitational yield about 2.25, 10 raised to minus 5. Whereas when you use hydrodynamic cavitation, it is higher, 6.7 into 10 raised to minus 5. So these numbers are just for comparing the efficiency under similar operating conditions, treatment conditions, say for same degradation, same reaction volume, 7 liters. Energy dissipation, of course, would be different because you're using centrifugal pump in one case, whereas in the case of ultrasound, it will be based on the generator for transferring your sound energy or ultrasound into the system. You can also compare rhodamine B. Typically, dyes is the most visible form of pollution. So definitely one needs to treat it because that's not good in terms of aesthetics. That's not good in terms of oxygen level in the water. So different configurations were compared, and you can clearly see plate 1, plate 2, plate 5 typically are for hydrodynamic cavitation, different plates in terms of the orifice uh, configurations. So plate 1 was highly efficient as compared to ACE horn right on the right side of the graph, where you are getting much lower effects in terms of cavitational yield. So typical nutshell comparison I'll give, hydrodynamic cavitation is definitely suitable for scaled up version, because if you look at the entire setup, your pump is the only energy transferring device. Acoustic cavitation is suitable at small scale. You can scale it up, but then there would be some issues in terms of operating cost. Energy efficiency is definitely high in the case of hydrodynamic cavitation. It's low in the case of acoustic cavitation. Flowability, yes, hydrodynamic cavitation can be good in terms of flow. It already has a pump, which is basic requirement. Cavitational intensity definitely is on a lower side in the case of hydrodynamic cavitation, and acoustic cavitation is on a higher side. So there are some advantages definitely for hydrodynamic cavitation, except for the last one, which says that cavitational intensity will be lower in the case of hydrodynamic cavitation. So I need to look at some aspects by which I can minimize my or maximize my cavitational intensity at minimum possible energy consumption. So either you can combine hydrodynamic cavitation with some advanced oxidation processes, or you can also think of combining hydrodynamic cavitation with acoustic cavitation, right? So that possibility is also there. Let's look at some environmental applications. Water disinfection and treatment is our theme. So again, earlier days, we also tried using hydrodynamic cavitation for water disinfection. Like you talk about bore well, there might be some microorganism present. So why can't we use hydrodynamic cavitation? Because again, in bore well, you have a flow where your water is coming from the Earth's crust into the surrounding atmosphere, and there definitely flow is there. So I can introduce cavitating device in the bore well, and then I can use it for disinfection. So some studies were done, total coliform skill, and you can see the effect of pressure here. So higher the pressure, you are getting higher disinfection. You can also apply it for seawater disinfection. Again, the destruction percentage is given. So under conditions, different conditions, so orifice plate or orifice velocity is different. So that can be varied based on your pressure. So orifice velocity is higher, meaning you have higher cavitational intensity, and there you are getting higher degradation or disinfection as well. So 100% destruction can also be achieved based on seawater. Now, seawater has an interesting application. Now, you might have heard about ballast water and need for treatment. So if I can scale it up, I can also use it for ballast water treatment. There were some talks initially, but haven't really been very successful because of a lot of complications involved. There, in ballast water treatment, definitely it has to be a single pass, because you can't keep on recirculating whatever water due to very high volumes. I really can't recirculate it for a number of passes. So single pass is a key requirement there, and then there were some problems in that. But yes, seawater disinfection was shown to be quite successful, and there you can use hydrodynamic cavitation. Let's take into some more case studies, and slowly we are going to move towards hybrid methods or combined cavitation processes. So degradation of reactive red dye 120. So again, dyes, because it's the most visible form of pollution. So this was tried, and we thought of introducing steam at the cavitating device. Steam again, just to give you some nuclei, and there you will get higher extents of degradation. So it was inserted at the venturi. So some initial experiments with steam, you are clearly seeing increase, but it's not very significant, right? It's providing some nuclei, but it has some limitation as well. So your 10% is going up to about 16%, but definitely very less as compared to a total degradation or elimination which is expected. So now we thought of combining it with hydrogen peroxide. I had said some time back that if you are having hydrogen peroxide, it can dissociate under cavitating condition into hydroxyl radical. So definitely you are going to increase the radical formation, and then you are expected to get beneficial effects. So let's see what happens when you are degrading dye in presence of hydrogen peroxide. Clearly, you can see that depending on the concentration which you are adding, you are getting up to about 90% degradation. So definitely hydrogen peroxide, it gives you many radicals in the system, and that gives you a higher extent of degradation. You can also think of applying hydrodynamic cavitation for distillery wastewater treatment. So distillery wastewater treatment, as you know, it has significantly higher COD levels. So if I talk about COD levels, about 35,000 BOD is quite low. So that's a big problem because biological oxidation, and this was one of the combined work which was done between NEERI, of course, and ICT under supervision of Professor Pandit. So I have taken that particular case study. So if you can look at biodegradability index, it's definitely increasing from about 0.1 to about 0.35. So biological oxidation, the key requirement is it should be between 0.3 to 0.4. If you have 0.1 as the initial BOD to COD ratio, definitely your biological oxidation is not going to be very suitable. So definitely hydrodynamic cavitation can be used as a pre-treatment, and then you can go to that particular desired range. So you'll not get significant COD reduction only in the pre-treatment, but what it's doing, it's trying to rearrange the complex molecules into simpler ones, which is clearly evident based on the increase in the BOD to COD ratio. And then you can get a good amount of degradation using biological oxidation. So that's the advantage when I'm talking about using hydrodynamic cavitation as a pre-treatment. I can also think of combining cavitation with Fenton. So in Fenton, again, you are having hydroxyl radical formation, but typically what you get is sometimes you are going to generate complexes which can be broken down based on hydrodynamic cavitation. So in this sense, you will get enhancement in the number of hydroxyl radicals which are generated. You can also eliminate mass transfer resistances if it is present, and that will also be quite advantageous. So it was a model system of, again, degradation of imidazole. So that is again a toxic compound, not very suitable for biological oxidation. So only SC, it was giving a rate constant of about 1.11 10 raised to minus 3. Only hydrogen peroxide, similar rate constant, but when you are combining it at different conditions of hydrogen peroxide loading, you can clearly see there is a significant increase in the rate constant. So you're reaching somewhere about 60 times or 50 times the initial value, and that is quite synergistic. So it's more than additive when I'm combining hydrodynamic cavitation with hydrogen peroxide. Of course, this is going to depend on system, so I can't generalize that for each pollutant I would get maybe 60 times or 100 times increase. Definitely, it needs to be evaluated at lab scale for different pollutants. So effect of Fenton reagent, the combination, it was increasing to about 190 to 44 times. So definitely combination is suitable. But beyond that, like if I want to also include photo, meaning UV irradiation, then it's not very significant because Hc plus photofenton is also giving you a rate constant of about 128 or 130. But earlier case with only Fenton also it was giving higher. So what I wanted to say here is that combining too many processes is also not a good idea. So you need to tailor that particular process, and somewhere you might get good results only on the basis of hydrogen peroxide addition. So I don't want to add Fenton, I don't want to maybe include photo, but depending on the system, of course. So if you're talking about something as a complex system, like a common effluent treatment plant where you want to treat a variety of chemicals which are present as mixtures. See, because in the academic studies, most of people would want to work on simulated effluent. So you take a compound, you dissolve it, that is your simulated wastewater, and then you get beautiful trends, but they may not be replicated when you talk about real industrial effluent. So that needs to be looked at. So if I'm at real industrial effluent, then it's a complex system altogether. There are too many compounds which are present, and then the treatment has to be differently thought about. So there maybe all the combinations are going to be quite useful. So just a nutshell comparison again, percentage degradation in 15 minutes, Hc plus photophenton was giving 100%, but even Hc plus penton is good enough because 98% degradation within the experimental errors is going to be quite similar, right? So I can just optimize my treatment scheme, and here I can just say that Hc plus penton is good. I can also think about advanced Fenton process, because if I look at the conventional Fenton, it is ferrous sulfate added with hydrogen peroxide, and there you also get a lot of sludge formation. And one of the ways to minimize sludge formation is to limit the amount of FeSO4 which you are going to add. And hydrodynamic cavitation definitely helps you in doing that. But if I can think of a system which is similar to your pack bed reactor, so I have a reactor bed which is containing iron pieces, and then again I have a recirculating system. It will be an advanced Fenton process, because in the feed tank you will have solution. You can also add hydrogen peroxide here. While recirculating, this hydrogen peroxide is going to come in contact with iron, generating hydroxyl radicals. So it's a kind of Fenton-like system. You will generate free radicals, but because this iron is not in dissolved state, your sludge formation is going to be minimized. So that is an advantage which you are going to get. So this was applied again for the real industry effluent, and the quantification was done in terms of TOC. So you are getting about 60% removal. The residual TOC was about 0.4, the ratio. So 60% TOC removal was achieved. And this was good because it was just thought about as a pre-treatment. So beyond that, you might have your biological oxidation, and then the treatment scheme would be very nice. So this is one of the projects which I worked with Ecosphere Technology. This is a US-based company, and we were thinking of developing a hybrid advanced oxidation reactor. So advanced oxidation, all of us know, it's going to generate hydroxyl radicals. Hybrid is you are trying to combine it and then achieve different oxidants in the system and try to utilize all the added oxidants to as high as possible. Then your cost of treatment is going to go down. So the system was in terms of combined operation of acoustic cavitation, which is ultrasound based, hydrodynamic cavitation, some amount of electrochemistry, and ozone. So your key advantages, if you are operating as a combined system, you will have lower dosage of ozone, you will have lower cost of treatment, definitely, because ozone is the most energy consuming device or oxidant in this particular system. You will have applicability to wider range of effluent and water streams. Why? Because you are having different oxidants in the system. So I'll have hydrogen peroxide which will be generated. You'll have hydroxyl radicals which will be generated. You're also introducing ozone. So ozone itself is an oxidant. If some amount of chlorine is present, say your application is based on presence of salts, then definitely you can generate chlorine-based oxidant. So it will give you applicability to wider range of effluent and water streams. And as I said, generating wider range of oxidants. So let's look at some of the expected benefits when I'm talking about different combination. So if I have cavitation in conjunction with ozone, you will have increased mass transfer due to acoustic streaming, which is liquid circulation introduced by ultrasound, introduced by hydrodynamic cavitation. Because one of the disadvantages with ozone definitely is problem in terms of mass transfer. So that is a significant advantage. You will have production of enhanced free radicals due to dissociation of ozone, also with reaction of ozone with hydrogen peroxide that is formed in situ. So definitely that's going to be useful. You will have combination of acoustic and hydrodynamic cavitation, which also gives you enhanced intensity of cavitational collapse. So definitely that's an advantage. So if I'm thinking of combination of ultrasound with electrochemistry, then again increased mass transfer, because your electrochemical reactions are also facing problems of mass transfer. So ultrasound turbulence will give you enhanced mass transfer, and you will have production of enhanced free radical. So this is the typical picture or schematic of the ozonics reactor. It has different zones. It has hydrodynamic cavitation, which is one. Ozone injection happens at point 2. Then you have a pipeline type reactor here, and then you have 4 as electrochemistry. So definitely I'm combining everything. And general specification. Now the original application was for treatment of frac water. So frac water is typically generated when you have oil exploration or natural gas explorations. So that water needs to be treated and recycled back. The problem is typically these oil wells have a shelf life. So I don't want to have a lot of capital investment there, because I'm not very sure in terms of how much long that particular operation would last. So definitely it can be a kind of a tailor-made application. So you just take your reactor, your trailer there, treat it for as long as it is required, and then that just can be moved elsewhere. Now, similar concept, the company also applied for some of the lake treatment options, because again, lake treatment, it would be seasonal, depending on where your algae bloom is there, or similar problems. So there also it can be thought about. So it has everything on board, like a diesel generator, you have cavitation reactor, flow loop, the electrochemistry units, and of course controls. And typically the radical reactions which are going to occur. So cavitation, you will have hydroxyl radicals, you have hydrogen peroxide. Ozone and cavitation, again, you will have combinations giving you hydroxyl radicals. Electrochemistry, of course, is going to give you hydroxyl radical. So depending on different components of the influent, a variety of oxidizing agents can be produced. As I said, fluorine might be present, especially if you are talking about the frac water application or seawater application. You have salts, so you can generate chlorine based on electrochemistry, and then hypochlorous acid or chloride or chlorine dioxide as of some of the oxidants. You also might have some content of permanganate, and that also can be an oxidizing agent. So these are, of course, the loading is going to be different. You will have majority of hydroxyl radicals, hydrogen peroxide would be there, ozone would be there. Again, some amount of other oxidants will also be present. So typically, when we started looking at it conceptually, we also did some theoretical simulations and trying to map your cavitational activity distribution in the reactor. Need to quantify the levels of turbulence, because what we have claimed is that you have turbulence, which is going to give you enhanced utilization of ozone, higher rates of transfer. So we need to look at what levels of turbulence you are generating. You can integrate it with chemical reactions for predicting the radical formation. And then you can also optimize the design and operating parameters. So basic equation for sound pressure field were used. You can solve it using CFD or COMSOL-based softwares. You need to just use finite element methods integrated with radical reactions which are likely to be present. And just some of the trends I'm going to show. So you will have uniform cavitational activity distribution throughout the reactor. Of course, there are some localized kind of high pressure fields, and that is the area where your transducer is located. So that is there. You have a lot of active velocity flow fields in the system. So that would account for pressure field and turbulence which is going to be generated. So I can look at different sectors of application for this reactor, and in general, hydrodynamic cavitation plus the Fenton or the hybrid methods. So you can look at pharmaceutical industries, you can look at pesticides, herbicides, insecticides, you can look at dyes and textiles, you can look at distilleries, you can look at wood finishing sectors, and everywhere you can treat your hydrodynamic use hydrodynamic cavitation for treating wastewater, right? So that's an advantage. You can also use it for microbial disinfection. So you can use it for water treatment, say a community groundwater supply. In communities, you can also use it for recycle of your say laundry wastewater. That can be treated and then recycled back. You can also use it in food processing industry as a replacement to thermal pasteurization. That is an advantage. Ballast water treatment, we have already seen it's a major problem in shipping industry. Because of microbial diversity, you cannot discharge your ballast water from one port to other without treatment. So onboard installations are going to be requirement. And as I already said, one pass treatment will be the key. Industrial cooling towers is one of the applications. So biofouling is a major problem because you normally use chemical biocides, but these offer disadvantages. And one of the common disadvantage is formation of scales on your heat exchanger surfaces. So that needs to be avoided, right? And you also have corrosion inhibition, scale inhibition. So you can use hydrodynamic cavitation and that gives you an advantage. You can use it for municipal wastewater treatment, like enhance the biodegradability of sludge. You can improve the sludge characteristics, improve sludge digestion, and it can be also integrated with biogas plants for municipal wastewater treatment or even on farmland projects based on agricultural residues. So that is an advantage. And you can typically enhance your biogas production based on hydrodynamic cavitation pre-treatment. Now, some of the success stories, as I said, for the ozonics reactor, it was mainly in oil and gas fields. So over 1,200 hydraulic fracturing operations, it was there and proven applicability at commercial scale. This is one of the pictures which was taken with the company people on site. It's not me, it's one of the company the representatives. But on the left side of your screen, you have the water which is going to come out, and then you need to treat it. And then after treatment, it's kind of milky because it was just taken right in the treatment. So you still have maybe some amount of nanobubbles. But I'm definitely not treating it for drinking water. I just want to recycle it and the purpose is served. So that is an advantage. Right, I can still think of maybe in next 2-3 minutes is already about 5:50, so we are right on time. So I just want to give you some idea in terms of how I can enhance my cavitational intensity. I can think of cavitation zone, like I can have one orifice plate after the other, after the other. Now, typical engineers would quickly tell me that you are going to increase your pressure drop significantly. But what I'm achieving is I'm achieving much higher cavitational intensity here. So you need to balance your requirement, and definitely it can oxidize your chemicals at a faster rate. But yes, I need to look at the pumping energy which is required. I can think of combining hydrodynamic cavitation with ultrasonic flow cell. So that is an advantage which I'm looking at. And because when you generate cavities using hydrodynamic cavitation, and if you collapse it under the influence of ultrasound, then the intensity of collapse is significantly higher. And that's the key advantage. Right, so just as a summary and concluding remarks, what we have seen is some guidelines in terms of optimum parameters, some reactor configurations that can be used. Definitely a lot of studies, a lot of publications from our group. Worldwide also, there are other groups which are working, which had shown efficacy of hydrodynamic cavitation reactors as compared to the acoustic counterparts, that is ultrasound-based reactors. These do offer potential for industrial scale application. Now, we have also tied up with many industries trying to transfer the technology and have been successful. So that is the current scenario. The operating efficiency of the circulating pumps, which is the only energy dissipating device here, is always higher at larger scales of operation. So that also gives you an advantage. So if you talk about higher scales of operation, definitely your pump energy is going, or pump efficiency is going to be on a larger side. So that will give you an advantage. Of course, when you are talking about hybrid methods, you need to really tailor it to a specific effluent and then arrive at the best optimum conditions, because then only your cost of treatment can be minimized. Right. So that's all what I wanted to say. And so Dr. Nidish, you can take it forward to the next stage. Okay. Thanks very much again for giving me an opportunity to talk here.
Thank you, Professor Gogate, for this wonderful talk.
Correct.
So next we can go for a panel discussion. Today we have three experts. Dr. Pawan Labshotter from CSIR-NEERI, Nagpur. Dr. Sujana MG from CSIR-IMMT, Bhubaneswar. Then Dr. S.T. Ramesh from NIT, Trichy. So first we can go for the questions from Dr. Pawan. Dr. Pawan, please raise your questions.
Yeah. First of all, thanks a lot, Dr. Gogate, for such a wonderful presentation. And you made it very, very simple.
Pawan sir, 1 minute. So Gogate sir, please, can you stop sharing
I'll
your
stop
slide?
the sharing. Yes, I'll do that. Right. Okay. This is good now. Yeah.
Okay, I just wanted to thank you. Means it was wonderful presentation. It was presented in a very simple manner. I'm pretty sure that everybody had liked it and got what actually hydrodynamic cavitation is. So yeah, I have a few clarification, but before that, I feel that it has really good application because I work mainly in water treatment, and I have also seen a few applications, particularly in disinfection. And Dr. Gogate, you might also be aware of a company which is based in Pune, and they make this cavitation devices, you can call it, and they fit into this Mark II hand pump. And then they claim that, okay, based on the cavitation, because in Mark II hand pump, you have to simply pump, and then the force is sufficient to actually produce cavitation. And they claim that this particular pressure, or say reduction in pressure, a high velocity might rupture bacterial cell, and then you can get rid of them. Yeah, but our experience is that whenever we have gone for evaluation of this particular technology, we still got some microorganisms or bacteria, E. coli, in say outlet water. And you also have mentioned about it in your presentation that the reduction in number of cells is like 60-70%, and when we are talking about these microorganisms to the scale of say 3 log, even if we are like 90% reduction, we still will have say 2 log of microorganisms in it. So I'm pretty sure that yeah, this is very useful technology. At the same time, we need to have some supplementary disinfection also. And chlorine is really good because it provides some residual effect, disinfection effect. So that's my comment on it. And second application which I realized, and I would definitely like to discuss with you about say transport. We transport bulk water from say reservoir through pumping station to our treatment plant. See, if you take case of Nagpur, we have reservoir of say 30 kilometers from the city, and the treatment plants are located very close to the city. And we pump this water, and when we pump this water, it comes with very high pressure, and we construct something known as a break pressure tank. And this is simply to bring down the pressure to level so that there's no say this a problem to our wastewater water treatment plant, in a sense that if it comes to this treatment plant at very high pressure, then it can break water treatment plants. We bring down this through break pressure, and then I'm pretty sure that we can say evolve some cavitation devices, maybe venturi based, so that this pressure can be utilized in creating cavitation, and then the microorganisms which are there can be reduced significantly. So that's one thing I really see as an application. So a few clarification, in fact, yeah. Is there any requirement for turbidity in water treatment which should be there before we actually use cavitation? Does it lead to say a substantial pressure drop or clogging of these orifices? Is there any requirement for that? Second is you were talking about say formation of this chloride and even hypochlorous, say, species during cavitation. So, is there any limit that how much should we say our total dissolved solid, or how much should be the chloride so that it also gets generated? Because we know that the disinfection might be occurring because of several phenomena. So that's another clarification I just wanted to have from you. And you really talked about pressure drop. So how can it be managed? Means you I think briefly touched upon it. So without wasting much of energy, how can we optimize? Is there any say, simple principle based on which we can devise this? So thanks once again for accepting our invitation. Thanks to Nidish also that he could get you. And with this, I would hand over to Dr. Gogate and request him to respond to my queries, and we can take forward the discussion. Thank you.
I think Gogate is having some internet having some problem now.
Oh shit.
He will join. He will join.
No problem. So we can take few more questions, or we can say proceed with discussion with Professor Ramesh and Dr. Sujana.
Right.
Or should we wait for Dr. Gogate to join?
I think he will join now.
Yeah.
Huh, sir. Sorry, I have unmuted. Okay. What about Nidish?
I don't know what happened. That is maybe some internet issues.
Internet issue or this thing. We can also discuss, sir. Sir, is it possible? Sir, it is to you, Dr. Pawan.
Yeah.
Can we take it this to the in the field conditions? Is it possible? Like
yeah, he's joining. He's joining.
He's there. Okay. All right. So, Dr. Gogate, could you hear whatever I?
Yeah. I think there was some problem in my computer, so it got disconnected in between. But now I have joined on the mobile, so I missed some of your comments. I think we were at the like transfer of water from reservoir to pumping station, and there definitely hydrodynamic cavitation can be thought about.
Yeah.
So sorry about that connectivity issue, but I'm back now.
Okay.
Right.
So, yeah, I was just commenting that you might have also heard about this break pressure tank which we construct upstream of water treatment plant. If we can utilize this particular pressure energy to create cavitation, because this lot of bulk water comes with so much of microorganisms. So if they can utilize, I think it will really be useful. The chlorine dose subsequently will reduce in water treatment plants. So that application can actually be thought. So I feel it's very, very useful. Yeah.
Correct. Yeah. So both, I think, in the Mark II, the hand water hand pump, and also in this pumping station problem, definitely hydrodynamic cavitation can be thought about as a partial treatment. It may not be a complete replacement, because definitely that residual chlorine is very useful for your drinking water application. But yes, if you're using hydrodynamic cavitation as a pre-treatment, your chlorine consumption gets reduced. So that is an advantage. So that way we need to think about combination of hydrodynamic cavitation with the chlorine-based treatment.
Yeah. So one more question was there. Do you have any because you were talking about say formation of this chlorine species also, like hypochlorite, hypochlorite, ions at all. So say I read about, I know about this electrolytic processes in which we can use different electrodes, and these species can be created. So is
Yes.
there any limit of say salt, or for that matter chloride in water, which will help us to generate these species? Means, have you worked on that?
No, we really haven't seen the effect of the chlorine content or the chloride content.
Yeah.
But in general, what we had seen is for the destruction of pollutants, the presence of chlorides help, because they give you a partitioning effect based on the salt characteristics. And there your pollutant is typically moved towards the gas liquid interface in terms of the cavitating bubbles. And then your degradation is better. So the presence of salts actually helps your cavitation efficiency as well in terms of treatment. And if you compare the combination with electrochemistry or the electrolytic processes, then whatever mass transfer again is a problem in that. So that also can be eliminated when you combine cavitation. So that advantage you can look at.
Yeah,
for
yeah,
the
great.
combination. Yes.
Yeah, last question was that you were talking about pressure drop.
Right.
Yeah. So, and secondly, see, suppose if you want to install it for water treatment, obviously, is there any clogging issue with orifices because of clogging? If highly turbid water is pumped through, so do you feel that there would be significant pressure drop, or we need to periodically clean up, say, this reactor?
Correct. So if there are solids present in the system, then definitely there would be some clogging issue. And there also might be some erosion of the cavitating devices, because finally, if you are having solids, it's going to bombard on the orifice plates. So their erosion is a possibility. So you need to have cleaning at periodic intervals, and just to avoid clogging, or if your the plates are getting eroded, then you need to replace them. So that issue might be there if you are having too much of solid content. But if it's like dissolved solids, then there is no problem. Only when you have solids of high size which are going to bombard on the orifice plate, then there is a problem.
Yeah. But just last question, Nidish. I'm sorry, it's so interesting.
It's okay.
Yeah,
Fine.
yeah. One more was like distally, and you had mentioned this improved, say, biodegradability ratio also. So what actually happens means are these organics get oxidized? Are they broken down? Particularly the chemical ones. So that it improves the body. What actually happens?
Yeah. So mostly, as I had said, it gives you a rearrangement of the molecules. So if you have complex molecules which typically cannot be oxidized by microorganisms, so those are broken down in the presence of cavitation into simpler ones which are easily biodigestible. So that way you get a significant change in the BOD to COD ratio, and then your biological oxidation efficiency goes up. So again, here also I am looking at cavitation as a pre-treatment to biological oxidation. So that is an advantage which you can look at.
Yeah, I think cellulose, because we find it very difficult to biodegrade. So that also can be really thought of.
Yes,
industry-based.
Yes, definitely. In fact, we are currently working with one of the companies, Aditya Birla, and trying to solve the same problem using hydrodynamic cavitation as a pre-treatment and also as a polishing step. So yes, that is also a good application which people can look at.
Okay, thanks a lot, Nitish. Over to you, and I will connect again with Professor Gogate, and then we'll discuss application in water treatment plant there and now. So
yes, definitely. Thanks very much. Yeah, thanks.
Okay, thank you. Ramesh sir, please.
Yeah. So good evening, sir. I'm Dr. Ramesh from NIT Tiruchirappalli.
Yeah. Good evening.
So good to see your presentations on basics of hydrodynamic acoustics for that cavitations and different types and other things and all. So I could have, I think I have two different the questions to be well, what about the reaction time in your reactor that plays because a major role in the degradation of any pollutants or what, because it's also a power intensive process. So can you at least brief us as to what could be the reaction time with respect to on different pollutant ranges? That is the number one. Yeah.
Yes.
Yeah.
So typically it will depend on what is the initial pollutant concentration. Of course, if you are talking about complex pollutants, then the treatment times are going to be higher. So
Yeah.
what we have seen typically, if you're using only hydrodynamic cavitation, it
Yeah.
can range from about 30 minutes to even 2 hours kind of.
Okay.
And as soon as you start combining it with oxidants, then
Okay.
definitely it can come down.
Okay,
So
sir, yes.
it can be as low as even 10 minutes if you're
Okay.
combining it with oxidants.
Okay, sir,
So
yeah.
that's the typical range. But again, as I said, needs to be optimized on a case-to-case basis.
Okay. Another thing is about the efficiency of the system mainly depends on your design of cavitation chamber. So that
Correct.
normally that you also mentioned like a different venturi and also orifice. And the shapes also plays a major role, if I remember correct. That is this
Yes.
triangular, rectangular, square, and also hexagonal.
Yes.
Is there any optimization study or anything on the recommended like shapes for the typical cavitation chamber?
Correct. So typically in terms of the circular orifices, that's very easy to drill based on the your experimental part.
Okay.
But what we had done a study based on theoretical simulations using the CFD, where you just have different shapes taken together. And there what we have realized that triangular holes are giving better results. But of course, we did not try for any experimental verification because of the lack of expertise required. So in general, if you are looking at commercial applications currently, you can just go in for circular holes. Of course, you need to have smaller diameter and large number depending on what orifice plates you are going to use. And that is the advantage.
Okay, sir. And you also mentioned like the typical different cavitation, transient and steady cavitation methods.
Correct.
For the, say, example, high strength and also microbial degradations.
Correct.
Is there any basis to select these sort of cavitation methods to apply on a particular technology or something?
Right. So, as I said, water treatment will require somewhat lower cavitational intensity, and there your steady cavitation is going to be easier.
Yeah.
So, venturi would be typically giving you the steady cavitation or lower intensity cavitation. So, that will be useful. Whereas, if you're talking about wastewater treatment, where you have a too high kind of COD, like I'm talking about distillery wastewater treatment, the COD runs into like few thousands or even lakhs sometime. So there definitely orifice will be suitable because it's going to give you more intense cavitation. Of course, the pumping energy and cost will be on a higher side. So that can be one of the factors which to decide whether you want to use orifice or a venturi.
Yeah. So what could be the possibility to scale up this reactor to the real implementation? Is there any limitations on the scale up, sir?
Scale up currently, cost of treatment is a limitation because industry are not really wanting to spend on wastewater treatment. So that's a common problem everywhere. But yes, because the ecosphere one, it was significantly at a larger scale because oil and gas exploration, the water quantity is significantly higher. So there it was operating quite successfully, but again, the target was there to kill microorganisms and decolorize it. So it was requiring again lesser intensity. There have been some installations even in CETP. So that also, because again, it's a common effluent treatment plant. So their spending is not a significant issue. You need to treat it and then the member industries are going to contribute. So that is there. But if you go into a local industry, the acceptability is not on a significant level currently due to the higher operating cost. So that we are looking at how to reduce it. And that's where your hybrid methods are going to be suitable. So that is a key.
Yeah. And even for, if you consider the wastewater as, say, example, domestic or industrial, and it may contain a lot of solids. Is there any prerequisites or pre-treatment methods to go at least start your cavitation actions or something like? Is there
Correct.
any
So if you are, so solid contained, as I just responded to Dr. Pawan's thing, if it's a hard solid, then it's going to give you some problem in terms of erosion of the plates or even clogging in some cases. So there you need to pre-treat it and then just separate out whatever solids are there. So if you look at industrial wastewater treatment, most of these would have a coagulation and that stage there. So after the primary treatment, just before your biological oxidation, you can very well use hydrodynamic cavitation, and then it would be the fitting into the existing system and useful also.
Yeah. So what could be the approximate cost, sir, in terms of 1 meter cube or, say, example, 1,000 liters or 1 liter? So what could be the approximate cost based on your experience?
About so treatment, again, it will depend on the operating cost, will depend on your actual COD levels or your microbial disinfection or something like that. The capital cost would be about 10 lakhs to 15 lakhs, depending on what pump sizes you're looking at. So that is the range.
Okay, so thank you so much. Nice
to
interact with you.
Thank you. Yeah, nice to interact with you. Yeah.
Sujana madam, please.
Good evening, sir. Myself, Dr. M.G. Sujana from CSIR-NEERI, Bhubaneswar.
Yeah,
very informative talk, very nice, and it is very informative.
Thank you very much. Yeah.
So, from your, see, this is completely new area for me.
Okay.
I'm working on water, especially for fluoride and arsenic removal from water, groundwater. So this is very, can we take this, see, most of your studies from your presentation, I can understand it is lab scale studies you have carried out. And any real, dyes also you have taken some textile industry waste. These are not synthetic material solutions you have prepared, are real systems you have taken. You have worked on real or synthetically prepared solutions.
So dyes and whatever like pharmaceutical pesticide compounds we have shown in the presentation, those were mostly based on simulated effluents, because as academicians we need to investigate the efficacy and then do some intermediate analysis, mechanistic studies. But the ecosphere one was definitely on a commercial level. The biodegradability index study was also based on a real distillery wastewater which was procured. And we have done some kind of analysis for a specialty chemical industry, and also one of the Aditya Birla study. So in general, yes, we have done a lot of studies and publications are also available, and it has been successful, and also slowly getting transformed into commercial installations as well. Like Ecosphere definitely is there. One of the prototypes has been transferred to Aditya Birla. Then one of the prototypes we worked with a Saudi Arabian company, and they were dealing with refineries. So spent caustic is a major problem there. So that we worked on. And lake treatment also. In fact, in Bhubaneswar, we also have a ICT campus. So there, along with Professor Pandit, they are working on a lake treatment project just to explore the idea. So that also is a possibility based on hydrodynamic cavitation and ozone. Right. So slowly it's picking up with commercial applications. Our group also has worked on a lot of real case studies and also closely with industry. So it will take some time, of course, to get into a matured kind of technology.
With real systems, if you work, you will know the real facing the different problems will be raised, and then that the technology will come to some stage where it can be applicable, real application.
Correct.
Another thing, it is cost effective. You are telling now. Cost savings. Capital cost will be like compared to the traditional methods, how it can be compared with the traditional methods like pesticide treatment.
And so,
my interest is for the drinking water. If we are going for pesticides, will be in the traces only.
Yes. So, pesticides can definitely be removed, and even your microorganisms which are there in drinking water can also be disinfected. Of course, as I just responded some time back, you will require some amount of chlorine because that will be your residual treatment. So in my opinion, it can be a good combination where your existing methods are there, but I can reduce the chemical consumption. So your costing would be favorable because it will definitely not be greater than your cost of chemicals.
Efficiency is important, yes.
Yeah, efficiency. And the combination also will give you synergistic effects, so more than the additive effect. So that is an advantage. So I'll not recommend hydrodynamic cavitation as a replacement, but it can be combined with your conventional methods, and then you will get your benefits in terms of higher treatment capacity as well as lower cost of treatment. So that angle definitely can be looked at.
And it can, as for a disinfectant, like chlorination is the practice in most of the parts of India, as we all know. Can we avoid this by using this HC technique?
So chlorination,
because byproduct during chlorination, they are just adding the chlorine. They're not saying how much is requirement of material balance. I don't know how they are doing. Most of the places, wherever we have visited, they are just adding. Thereby, byproduct formation is there, and then it is creating many secondary contaminants into the water. So we can avoid that by if we take this technique into the real real water systems. It will solve that problem.
Yes. So there will be two angles in this. So if your water is going to be utilized quickly, then definitely I can think of a replacement, because hydrodynamic cavitation can give you same treatment efficiency as compared to chlorine, but the consumption needs to be quickly looked at. So if you are just looking at a society treatment unit where water is going to be used daily, then this can be a good replacement. But if you are looking at, say, a pumping station, then it will also require some amount of residual oxidation capacity. So there hydrodynamic cavitation will be used, and in addition, some supplementary chlorine also will be required. One of the applications where chlorine has found a replacement is in your swimming pools. So it's not in India, but in Western countries, I know of some application where swimming pool treatment, water treatment, hydrodynamic cavitation can be a good replacement to your existing chlorine.
That is also good, yes. The swimming pools also, they add a lot of chlorine, which is not required. So much of chlorine is not required. They add just, they dump.
Yes, yes. So there the hydrodynamic cavitation can definitely be a replacement, because their water also can be treated and recycled back and reused back.
But I guess it may not solve the purpose for future contamination. Well, say example from the treatment plant to a consumer, and for during their the distribution, it may not solve the purpose. I guess you can do it on-site.
So it will be an on-site treatment. Definitely, it will not have any residual effect, which is definitely obtained in chlorine. So that angle needs to be looked at.
Thank you, sir. Thank you so much.
Thank you. Thank you. It was nice interacting with you.
Thank you, madam. So, Professor Gogate, I have two questions. One is you said in seawater treatment, you can go for disinfection of seawater treatment. So one reaction with hydroxyl radical is if it is chloride is present in the water, especially the high amount, it will undergo the redox reactions with chloride. So you will get definitely final product is OH minus ions plus chloride radicals. So what will be the exact oxidant for microorganisms, that means disinfection?
So it will be again chlorine radical based, again can give you like chlorine gas as a possibility, but mostly it will be still based on the hydroxyl radical, which is a dominant generation. So that also will be mainly, so it will be basically a combination of hydroxyl radicals plus chlorine gas, which can be formed in situ, and even chlorine dioxide. So we haven't really quantified the individual generation, but as I said, in the frac water recycle, these are some of the oxidants which are likely to be generated and acting. So a basic study can very well be done in terms of quantifying different oxidant productions. So that we haven't done, but yes, that there is a possibility in that.
Okay. So next question is on, you mentioned about ballast treatment, water treatment.
Yes.
So there will be a lot of oils. What will be the effect of these oils on hydrodynamic cavitation?
Correct. So if oils are present in high quantum, then they will have basic alteration on the viscosity. So then your hydrodynamic cavitation efficiency will be reduced. But if it is in minor content, then I don't see much of problem in terms of the hydrodynamic cavitation efficiency. Only thing is where the viscosity changes significantly, then your cavitational intensity will be lower. But otherwise, there should not be much problem.
Okay, thank you. Thank you, Professor Parag Gogate. I think questions are over from experts panel, from the experts and from my side. Students may have some questions. They may raise their questions in the Facebook. I will collect all the questions and will send you maybe today or tomorrow.
Okay, fine. So I'll be happy to reply. And then it was nice interacting with you all, and it was a good interaction.
Yeah.
Of course, it's thanks very much.
Thanks.
Thank you, Professor Parag Gogate, for this wonderful lecture, because he started with the basics of acoustic cavitation, then its experimentation part, modeling, then its implementation part. Finally, he last week, 2 days back, Professor Muthupandi and Ashok Kumar, he explained about the acoustic cavitation. Now, today he compared both. What will be the effect? What will be the advantages and disadvantages? Of course, it's a wonderful talk. Thank you very much for accepting my invitation in the first email itself, and for giving a wonderful lecture. I think most of the students will be benefited by this talk. And I also thank all the experts members who joined with me and giving this program very wonderful by giving or sharing their thoughts and making the interaction effectively. Thank you very much for everyone for watching this program. So tomorrow, 5 o'clock, again, same time, 5 o'clock, Professor Carlos Martinez Futil from Brazil will join with us. He will discuss about electrochemical treatment of water and wastewater, which basically may give in the mechanisms of all the electrochemical methods. Thank you for watching, and thank you very much. Thank you all.
Okay, thank you.
Thank you so much. Thank you, Dinesh. Thank you, Pawan sir.
Yeah, thank you.
Thank you, sir. Thank you so much.
Thank you, Gogate sir.
Yeah, thank you. Bye.
Thanks a lot.
Bye all.